back. We're going to talk about a lot more exciting math today. But first, a slight change of pace. As promised last class, I'm going to go over the assignment first. You may notice I'm on the pewter. That's crazy. That's because I have a couple things to demonstrate about running the assignment that, well, Apple won't let me do on this. So to get to the assignment, this part should hopefully be pretty basic. Go to Content, and then Assignments, Assignment 1. So far, so good. Hopefully you've already looked at this a bit before this class, but this is a good opportunity to get another overview of it and get any questions you have answered. So it's due on next Friday, and this is honestly my least favorite assignment of this course. Every other assignment has a pretty clear theme or like central concept to it, but it's just math and a barely relevant Java coding exercise. Very much worth pointing out is that there are two formats of questions on this assignment. Written questions, which will involve proofs and, in later assignments, more conceptual stuff. Written questions will be handed in on CrowdMark, whereas coding questions will be handed in UMLearn. It can be a hassle to work with those two platforms at once, but each platform is just better suited for certain types of files. Can't really get around that. The two main things I wanted to demonstrate are that while you're certainly allowed to write your written questions on paper, you'll get one bonus mark if you do it electronically. Make it look something like this. Actually, I'm going to make everything bigger. Hold on. Okay, hopefully this looks nicer. You'll get a bonus mark if you do it electronically, and I'll demonstrate this by doing the first example of today's lecture electronically. And then on the coding question, I want to really emphasize that the markers are going to run this code from the command line, and that if the markers can't run your code on the command line, you can very well get a 0 on that question. I'm aware that not everyone is familiar with how to use the command line, so I'm going to do a demo of just a minimal example, how to navigate to the folder that contains your .java file and run your program on the command line. These first two questions are sort of examples of why I don't like this assignment as much as future ones. This has nothing to do with data structures. It's not even going to build a foundation for data structures or anything. It's just math practice. Of course, it is practice for math that will be foundational to data structures, but ultimately, it's just math. These two, question 2, parts A and B, are tricky because they're true or false questions. In addition to the burden of making a proof, you also have to figure out if the statement is even true. Luckily, question 3 is more straightforward. These statements are definitely true. If they're not, I've screwed up, and they better resemble the stuff we've done in class. Oh, and question 1 is just using mathematical notation. All right, so the fourth question is the coding question. And it's going to be easy unless you're unfamiliar with Java, I think. You are given code, and you just have to translate this into Java. The goal of this assignment really is just make sure you have a working programming environment before I give you actual problems. So now I'll demonstrate how to run this program on the command line. This will be a bit Mac specific, but the two commands that you'll need to use to compile and run your code will work regardless of platform. And I'll make it clear what parts of this little demo are specific to Mac and what parts are universal. So first you're going to open up your terminal. In Mac it's called terminal. In Windows it could be called anything from Windows terminal to command prompt to PowerShell, probably a couple other things. And on Linux it's probably also called terminal. Next, you'll want to navigate to the folder that contains your Java code. The universal way to do it is cd, that's change directory, and then type in the path to the file you have. So /users/ that's me. So kit/2140, but I'm already exhausted. I can't do this. On Mac, you could start typing cd and then just drag the folder that you want to open into the terminal, and that'll give you the path right there. I'm sure a similar shortcut exists on other operating systems. Press enter to execute your command. The terminal is now in that folder. This is equivalent to using your file manager to open up a specific folder. And here's the code that I want to run. To compile it, I'm going to type java c, Java compiler, kit Zoe A1Q4. As always, I'm lazy. I don't want to type the whole thing. You can press tab to autocomplete commands. If there's only one way to complete a command, that if I keep typing go q4.j, there's only one file whose name starts with kitzoe a1q4.j, and I can just tab to type the rest automatically. So Java C to compile, press enter to do that. Then after you've compiled, do Java C, and then the name of your file again, kind of, except without the file extension. This is just going to be your last name, first name, A1Q4, and that's it. So that's how you run Java programs in general, but there's one more wrinkle to this specific assignment, and it's that it takes an input file. So you'll have to give that input file as part of your command. This command is set up for an environment where the file a1q4test.txt is in the same folder as kitzoe a1q4. I don't have it set up like that. Don't worry, the markers will. So I'm going to have to type in the full path to that file. Like that. I'm just going to press tab. So Java, class name, input file name. And then it'll write out something like this. So yeah, I don't want to shame anyone who has trouble with the concepts and the statistics stuff that you're being told to do. But the goal of the assignment is not to be a challenging coding exercise. Those will come later in the course, believe me. The goal of this part of the assignment is to give you a refresher on how Java works and make sure that you have a solid foundation to start doing actually difficult programming problems later in the course. Of course, stuff like installing Java and getting file input to work very well may be difficult, but that's the point. Hello?
Sorry.
It's all good. And then question 5, we'll do something that we're going to talk about tomorrow, analyzing the time complexity of an algorithm. Of course, we'll get into this tomorrow, but what this means is to use some cool mathematical techniques to express how long the algorithm takes to run in terms of its input size. So obviously our algorithm for figuring out the mean of a data set is going to take a longer time for a larger data set. That's intuitively true. But how exactly will it take longer? How much longer will it take on a large data set? That's what you're going to figure out on question 5. So let's start talking about the lecture content. We're going to sort of take a wild turn elsewhere to talk about summations briefly before going back to proofs with quantifiers. Hopefully you've read the readings or saw summations before. This is yet another example of, I'm going to assume you know at least a bit about this. But yeah, we're doing summations. This S, k equals 4, 10, k squared plus k means to add up the values of k squared plus k for k equal to 4, 5, 6, 7, 8, 9, up to 10. Later in this course, and by that I mean tomorrow, we'll see how summations are used in computer science, and we'll find that a summation that looks like this with a variable that doesn't start at 1 is very inconvenient, very bad. And we will want to re-index it so that the variable starts at 1. All of these possibilities have the variable start at 1, but only one of them does that well. Which one does it well? Well, as seen in the readings, we have a technique called re-indexing a sum, and that's basically to make the variable start at a lower value, but then add or subtract to the variable to make it so each value that it takes on is equivalent to a later one. So like when k equals 1, we get an answer equivalent to when k equals 4. When k equals 2, we get an answer equivalent to when the old k equaled 2. So each value of k is going to be subtracted by 3 in terms of its actual value, but then we're going to add 3 to it whenever we're calculating the value of that expression. Expression D fits that description. We make k go from 1 to 7 instead of 4 to 10, subtracting 3. And then we replace k with k plus 3 to counteract that. These two expressions will end up getting the same value, and this technique works in general. Now for the cool part. I'm going to show off what you can do on this assignment to get a bonus mark. I mentioned on the assignment outline you could use tools such as Markdown or LaTeX. I'm going to show off Markdown because it's simpler to use, Using LaTeX won't get you any more points, but it might make the marker like you more. Whatever. So I'm going on my desktop, going to make a new file. Cool example, .md, markdown files end in MD. And then I'm going to start typing and show you how Markdown lets you use this math notation. So the correct expression is D. And then to start typing in math stuff, I'm just going to zoom in too. I use a $sign, and then everything within, or everything between $signs is going to be rendered mathematically. So S equals, and then you're going to use a bunch of different sort of commands in Markdown and LaTeX. The first one I'll demonstrate is that \sum will render to this big sigma symbol. And then it has its own specific syntax. I'm going to do underscore curly bracket k equals 1, caret squirrely bracket 7. This is good so far, but I want to see what it's going to look like in the end. So I use this button to open up a preview. I think this is built into Visual Studio Code, but it might require some extension. If you're not able to see this button after a bit of fiddling, talk to me about it. Now we have our preview, and we see that the sum and the mess of underscores and curly brackets has rendered as the actual notation that we wanted. So I'm just going to keep typing. The rest of the expression will be a lot more straightforward. 2 brackets, k plus 3. To write an exponent, I use the caret and the number that I'm raising the expression to, plus k plus 3. Yippee! So we end up with something like this. And then depending on the tool that you use to create your assignments, actually getting them onto CrowdMark will look different. When I first started typing out assignments like that, I would just take screenshots of the VS Code window, and that'll work. The markers won't get that mad. But there are better tools available. I'm just using VS Code because it's the most common and simple. I recommend using Obsidian if you're going to get really into writing with Markdown. So I think that's everything I wanted to talk about with the assignment, and is also a convenient start to the lecture. I'm going to move the lecture over to the iPad and set up the recording again, so there will be a very quick break. While I'm doing that, feel free to ask any questions you have about the assignment. Here's another exercise to do with summations. We want to simplify a sum until no summation notation remains. This is going to be something that you'll eventually realize is useful. as is all of the content that we've seen thus far. When expressing how long an algorithm takes to compute, this summation notation isn't really that useful, and so we want to simplify it. We're going to use these identities given below on the slide. If you're ever asked to do something like this on a quiz, which might happen tomorrow, there might be something like this on the quiz tomorrow, I'll give you these identities. No need to memorize them. So first step to solving anything like this, just rewrite whatever you were asked to solve. And remember, our goal is to get rid of this summation notation. We don't want to see that. We have these identities that let us do that, but notice that they are all for sums that start with 1. This, in my opinion, still isn't a very good motivation for why we want to reindex summations, but it should be a bit clearer now. We want to reindex summations so that we could use these identities more easily, so we can simplify more easily. Why do we want to simplify? Hopefully you'll find out tomorrow. So I'm going to do something similar to the previous example. J is going to be 2 less than it originally was for the actual values that it takes on. But then in the expression, we're going to add 2 to J to counteract this. The result will have the exact same numerical value, but just be more convenient to work with. I'm going to skip a step for the sake of just moving along with the example. We can see it in the slides that we do some algebra, like simplifying these things into all this. But it's just algebra. You came here for me to teach you about computer science, not for you to watch me do algebra. So I'm going to skip to the next part in which I can do some computer science. Okay, we have a summation that starts with its summation variable at 1, but we're not quite at the point where we can use these summation identities. We have something for when the summation is just j, for when it's j squared, and for when it's 1, but not for when it's 2j squared plus 13j plus 19. So we can use some properties of summations. These are given in more detail in the readings to split up the summation. just because of how addition works, like, I recommend looking at this on your own and like making examples and convincing yourself that this works. We're able to turn this one big sum into several smaller sums, each with one term. Another trick is that we're able to sort of extract constant multiply. This just uses the distributive property. To do something like that. This sum of 2j squared turns into 2 times a sum of j squared. And now we're at the point where we can actually use those summation identities we talked about earlier. So 2, we keep the constant multiple. And then I check the summation identities that I'm so graciously given. We're going to use this one. But a word of caution is that these are used for counting up to a variable n, but we're counting up to n minus 2. But we deal with this exactly as we might expect. We just replace n with n minus 2. Ooh, I forgot to put j there. Next up, we simplify this part using a very similar idea. Keep the constant multiple, and then use the summation identity, just replacing n with whatever we're actually counting up to. And then this summation identity for constant, interestingly, doesn't require you to count from 1. So I guess we could have like separated this 1 from the rest and then only re-indexed the sum for these terms, but like, whatever. It works either way. Using the expression in the summation is going to simplify to this. And then we're done. That last line might not really look that much simpler than the line before it, but, and I'm gonna keep saying this, later in the course this will be useful because we can glean some properties of the expression much more easily from that last expression than from the second last expression with the summations. You'll just have to wait to find out why. So solution 1 is exactly as I did this. Solution 2 shows another method to solve these sorts of questions. Before we re-indexed the sum, subtract 2 from the variable's actual values, and then add 2 to the variable when you use it. Those two things cancel each other out and make it so the expression has the same value, but it's easier to work with. Another thing you could do is count up from 1 to n instead of from 3 to n. Oh my gosh. Dang. So counting up from 1 instead of from 3 will introduce some terms that'll make the expression bigger than it was before. But now you can just counteract it by subtracting your expression from 1 to 2. I personally prefer this method. It's nice. I don't like reindexing sums. But both of these are valid. They end up with some different looking algebra like near the end, but they are numerically equivalent. If you happen to have a question like this on the quiz tomorrow, which you might, either solution would work. Okay, hope you didn't miss quantifiers too much, because we're going to keep talking about them. But if you excuse me, I'm just going to add another page. Maybe I should do this before. Yeah, actually, I'm just going to add 2 more pages because I know we're going to do 2 more exercises. This is going to save us like 15 seconds. Very efficient. Oh wait, we have even more. Huh. Okay, that should be it. So where even were we? Around here. We're going to prove the statement there we go. We're going to prove the statement that for all m greater than 0, there exists n greater than 0 such that n is strictly less than m times n squared minus 1. Whack. We're going to see another trick for dealing with inequalities, but before that, we just apply the techniques we always have. Our proof is going to start with let n equal something, and we want to find out in some rough work, what should we do about n? So we rewrite the inequality that we want to prove and just mess around with it. Here's the trick that we're going to show off this time. I'm going to factor out a large term of the more complicated side, and that's going to help me simplify it. So now we're going to have n is less than a factored out n squared times m times 1, because that's n squared divided by n squared, minus 1 over n squared, because that's 1 divided by n squared. So we kind of just made it more complicated, but whatever. This gives us a much easier path to eliminating the multiple terms on the complicated side, because we have this little thing, 1 minus 1 over n squared. And remember, we're just exploring, trying to find a value of n that'll make this whole thing work. We can just guess. And once we do guess, I want to find a value of n such that this whole thing will simplify to a constant. And then once this becomes a constant, this becomes all one term and we'll be very happy. So how are we going to turn 1 minus 1 over n squared into a constant? Well, obviously by making n into a constant. But we'll want to be very smart about how we do this. We want to find an n such that 1 over n squared is less than 1, because that will make it so 1 minus 1 over n squared is a positive constant, which will be much easier to work with given the restrictions that m and n have to be greater than 0. So positive. I'm going to say n equals root 2 perchance. You can't just say perchance. And then this is another weird thing that students can and will get confused about. I substituted a value for n just now, but I only did it for one of the n's. Aren't you supposed to substitute everything when you substitute something? No. You can do this, you're allowed to. I don't really have a more formal explanation for that than this. We choose to only substitute our value for one instance of the variable, just because it's going to help us solve for that variable later. So let's simplify this, just do some more algebra. Root 2 squared is 2. The thing in the brackets is now 1 minus 1/2, which is 1/2. Cool. We're very close to solving for n. This is just some more straightforward algebra. Also remember that thanks to the order of the quantifiers, m exists when we define n. So we can define n in terms of m. So I'm just going to divide both sides by n to get rid of that squared and the n on the other side. Move everything except n to the other side so we can isolate it. Okay, we have n greater than 2 over m. Sweet. I'll keep emphasizing this. This was just rough work. We haven't proven anything yet. We've just found that if we assume the inequality we want to be true, then we find some nice properties of n. And since our proof is going to involve us choosing values for n, we just use those values that we found might be useful. So before I get to the formal proof, I wanted to note that choosing n is going to be a bit more complicated still. What order should I do these in? Right, I know what to do first. So in the past, we've had situations where we guess like n should probably be greater than root 5. Sure. And then we also find that n has to be greater than 9. Okay. how do you reconcile those? How do you let both be true? Well, you just let n be greater than 9, because something being greater than 9 automatically makes it greater than 5, because integers are ordered. That's crazy. But in this case, I meant to write n is greater than root 2, because we're guessing bounds on n, not actual values. Sorry. We have that n needs to be greater than a specific value, root 2, and that it has to be greater than an expression that has a variable in it. That screws up our whole idea of ordering. We don't know whether 2 over m is greater than root 2 or not. So how do we manage this? We're going to let n equal, and then use a function called max. The max function takes a set of numbers, actually a set of any object that can be well ordered, but whatever, and returns the largest element of that set. So we're going to give it root 2 and 2 to the m. And wabam. This max function doesn't work like functions you might be used to, because it doesn't calculate an algebraic expression based on the variables it's given. But it's well defined. There's never any ambiguity as to what it does. So it's a thing you can use. So between root 2 and 2 over m, whatever of the two is greater, n will be equal to that. But that doesn't quite guarantee that it's strictly greater than both of them. It's going to be greater than one and equal to another. So we need to just bump it up a tiny bit to guarantee that it's going to be greater than both. N equals max of root 2 and 2 over m plus 1. So whatever value turns out being bigger, n will be slightly bigger than that. Okay, last thing before I go to the formal proof. It's that my choice of root 2, which I personally prefer because it makes this substitution of like n squared turning into 2 a bit nicer. That is different from what the proof in the slides uses. Uses a very similar technique, but with 2 instead of root 2. We discussed this a bit earlier for like 5 versus root 5, and the effect is the same. If you guess that n should probably be greater than 2, it'll also be greater than root 2. And all of the math that I just did will work in the exact same way. You'll still be able to say that 1 minus 1 over n squared is less than 1 minus 1/2, just because of the ordering of the numbers. In fact, the slides use 2 instead of root 2 purely because 2 is a bit easier to type. So I'll keep mentioning the values I'm using are not the only possible values that you could use to prove the statement. Indeed, anything greater than the bounds that I found, like root 2 and 2 over m, is guaranteed to work because again, just because of how the numbers are ordered. And you can probably find values that are smaller than the ones that I used that still work. So now that we have a choice for a value of n, next up is the formal proof. This is the sort of thing that you would write in a completely hypothetical quiz tomorrow, if that question like this appears on a quiz. Let m greater than 0 be arbitrary. Let n be the thing we found out probably works. And then show that it's true. I'm going to kind of gloss over steps 2 and 3 in order to ensure that we can keep moving through the lecture. But step 2 essentially explains why step 3 is able to work. And then step 3 just goes ahead and does all the algebra described in step 2. When you're studying, I recommend looking through proofs like this, going through all this wacky algebra, and then making sure you understand every step. Like this 1 over n squared turning into 1 over 2 is derived from the first sentence of step 2. Figure out that sort of thing for the entirety of step 3 on your own. The general strategy for this, like I mentioned yesterday, there's several tricks to this. So this is the factoring out trick. Put this next to the rounding up trick if you're writing notes like that. And it basically comes into play whenever you have an inequality with a variable minus a constant in a set of brackets. And you just factor out the largest term of that set of brackets to end up with an expression like this. And then you choose values of n that make it so the set of brackets is bounded by some constant. And bam, then you went from 2 terms to 1. I like that last sentence in the slide. 1/2 is a convenient choice, but we could have picked any positive constant strictly less than 1. So if we were in a situation like this, it would have been equally valid to say, like, maybe n is greater than root 3, and then that would turn into 1 minus root 3. Sorry, 1 minus 1 over 3. And then that would turn into 2 over 3. And then we'd get a final expression that looked something like 3 over 2m. Sure, that would work. These are inequalities, not equalities. So there are lots of different values you could use. Yep, just do more algebra and then you get a simpler problem. Woohoo! Okay, this one is gnarly because as we've been doing throughout these problems, we've had a complicated side and a simple side where complicated just meant 2 terms and simple meant 1 term. This time, they both have 2 terms. They're both complicated. So we're going to have to find simplified forms of both sides. And it's going to be kind of annoying. Whatever. was going to write the entire statement, but I think it's unnecessary. We just need to be able to refer to the inequality. Actually, I'm going to rewrite the whole thing because I want to be able to see the quantifiers. Sick. So for n squared plus 6, we want to find a simplified expression that is greater than that in order to fit between the two sides of the expression. And that, thankfully, will be pretty easy. If we make it so n is greater than square root of 6, then this whole thing is going to be greater than a simpler expression. And as usual, there's a style difference. I like to use square roots when dealing with squares because then it's more obvious what we're actually doing, like with these squared terms. But the formal proof in the slide uses the actual value 6, and that still works because 6 is greater than square root of 6, and thus our algebra works in the same way. Now to simplify the other side, m times n cubed minus 5n. We want to find an expression that is less than that in order to fit between the two sides of the inequality. And for that, we're going to use the rounding up trick. So I'm going to factor out the largest term in that set of brackets. And then 5n divided by n cubed is going to be 5 over n squared. And then I'm going to use the same general strategy. I want this whole thing to turn into a positive constant. So I'm going to choose n such that 1 minus 5 over n squared is something convenient. Something convenient often happens to be 1 over 2. So how do I make 5 over n squared look more like 1 over 2? I'm going to choose n equals root 10. But I'm going to guess it. This is rough work. Come on. We substitute that only for the n that's inside the brackets, because we can. We square the root 10 to be, yeah. Oh, crap. I did the exact same mistake that I did earlier with root 2. Thanks for catching that. Also, a bit more exposition on why we use those signs. Using equals could maybe work for a simpler proof, but we're often dealing with multiple different conditions. So if I said n is equal to root 6 and n is equal to root 10, that would be impossible. A number can't have multiple values. But if we guess that n is greater than root 6 and greater than root 10, cool. We just say that n is like root 10 plus 1 or something. And both of those are true. So anyway, root 10 squared turns into 10. 5 over 10 turns into 1/2. 1 minus 1/2 turns to 1/2. And we get something nice. So now we have sort of expanded inequality that looks like this. We know for sure that these two parts are true. And then this inequality here is difficult to justify, but like, trust me, bro, this works. Basically has to do with transitivity of these inequalities. If this is true, then it implies the other two inequalities. So in the spirit of assuming the thing we want to be true is true, and then finding out a value for n that works for that, we're basically going to assume that that middle inequality is true. I don't like how hard that part is to explain. It feels wrong, but it ends up working perfectly every time. So 2n squared is less than 1/2 mn cubed. And I have the feeling we're just going to be able to, oh yeah. Yeah, it's in the spirit of making it so there's only one term in each expression. So if we only simplified this side, we'd end up with an inequality like this. And then any attempt to solve for n with this would be horrifically clunky, just because of the multiple terms. You could honestly try this yourself and find that solving for n with something like this is a lot harder than solving for n with something like we have on the left. Does that answer your question? Cool. Yeah?
Sorry, is the greater than sign up there on n squared plus 6 squared and n squared plus n squared, is that supposed to be less than?
Ooh, let's see. Over here?
Yeah.
Let's see, probably. Totally. Yeah, good catch. In addition to the greater than sign just, being necessary for big inequality to work, You might have also noticed that it's necessary for that to work with n being greater than root 6. That's different from what I had before, right? Huh. Weird that the undo and redo functionality seems to just break near the end of every lecture. Whatever. We have less than. Back to what we were doing before. We want to solve for n and make it in terms of m, just because we know that we're choosing a value for n and we already have m defined. So let's do this. I'm going to divide both sides by n squared to make it so n only appears on one side. And then I'm going to divide both sides by 1 over 2m to make it so n is alone on its side. It's nice how these problems eventually reduce to middle school algebra after you do this mind-bending second year weirdness. Cool. So this sort of completes our exploration of n. We have that n needs to be greater than 6, n needs to be greater than 10, and n needs to be greater than 4 over m. Since 4 over m isn't a constant, we need to use the max function to make sure that we choose a value that's greater than all of these. But for root 10 and root 6, I know that root 10 is greater. So I'm just going to do that. It would not be a mistake to write that it also has to be greater than root 6, but it would be redundant. May as well also say that it needs to be greater than 0. Oh, undo and redo work again. Nice. And then to guarantee that it's greater than, not just greater than or equal to, all these, plus 1. Again, the formal proof just uses a value that is it uses a natural number for simplicity, but I used square roots for sort of its own kind of simplicity when dealing with squares and square roots. They both work. And again, I'm going to gloss over the formal proof, even though the formal proof is the part that's worth marks, because I've shown you how you would be able to write the formal proof, because there's a lot of weight borne. What I'm trying to say is that the value given to n is sort of load-bearing. There's a lot behind it, and I've shown you what's behind it. The rest is sort of doing our rough work in reverse and finding or explaining properties of n that allow us to start at one side of the inequality and arrive at the other. Also, like the previous example, I recommend going through this last step and making sure you understand how each step follows from the earlier step. Yeah, this doesn't look immediately intuitive. We don't really know how, or it isn't immediately obvious how you get from m over 2n cubed to 2n squared. But it's a consequence of our definition of n. So connect each part of that algebra at the end to the explanations given before it. In the interest of time, I'm going to skip past this example. Well, not going to completely skip it. I'll gloss through it. All this one really introduces is the rounding trick with even more terms. We have this expression, and it turns out that the best way to deal with it is to factor out n cubed, largest term, or largest degree of n inside of the set of brackets. We end up with an expression that looks something like this. And then a slightly more complicated version of what we've been doing with the value 1/2 follows. We need to find a value of n that makes it so 2 minus 3 over n squared minus 1 over n cubed turns into a nice value. And then the rest is as expected. I think I would probably use the square root of 6 so that this turns into 3 over 6, turns into 1 over 2. And then you could do whatever you want with this, but it definitely won't cause this whole thing to become less than 0 when subtracted from 2. Yeah?
Just like earlier, you could assign different values to each of those n's?
No, n is just one variable. You would have to only give one value to n like at all, but you can still take advantage of inequalities and substitute different values for n to different instances of the variable, as long as all your inequalities hold. So I think I might end up just doing this example. If you want n to be greater than root 6 to turn this into 3 over 6 into 1 over 2. And then you also want n to be greater than the third root of 2 in order to make this into 1 over 2. You'd end up with 2 minus 1/2 minus 1/2 equals 1. You can do that. Just make sure that you set n to something that is greater than all of these. You could do something like 3, and it'll just work. Something this complicated might come up on an assignment, but won't come up on a quiz. We've passed the difficulty of the difficulty level of the quiz a little while ago. However, this slide I wanted to skip to because it also contains something that might be on the quiz. And that is negating logical expressions. Don't think I'll be able to get to the end of this example. To be honest, in future lectures, I'm going to be doing a lot of cherry picking which examples are going to be the most useful for the class, and then you could do the remaining ones on your own or talk to me during office hours. But wanted to use the last little bit of time to talk about disproofs. Disproving a given statement is logically equivalent to proving its negation. We already talked about negations a little bit in an earlier lecture. In particular, we talked about quantifiers. If you want to show that something is not true for all variable or for all values, you show that it's not true for a specific value. So turn a universal quantifier into an existential one. And vice versa. If you want to show that something doesn't exist, you show that it's not true for all possible values. The big thing, and like this will like directly translate to a mark on the quiz, maybe hypothetically. When you're negating a inequality, you have to turn a strict inequality into a non-strict inequality, and vice versa. Because before, mn cubed was less than that, so it was like somewhere on the number line to the left of it, but we know that it wasn't exactly there. Can't be. What's the opposite of that? The opposite of mn cubed being strictly less than n cubed plus 2n is it being greater than or equal. If you don't get what I'm saying, I recommend playing around with it and think about it in terms of numbers rather than expressions. It's much easier to talk about, say, a number being strictly less than 5 or not being greater than or equal to 5 than it is to talk about mn cubed being strictly less than n cubed plus 2n. The takeaway here is that you turn a strict inequality into a non-strict one. Cool. Anything else I wanted to talk about? I guess it's worth noting that the conditions on the variables remain the same. When you want to negate a statement saying that something is true for all m greater than 0, you're still talking about things, or you're still talking about values of m being greater than 0. You change the quantifiers and the inequality signs to make those opposites, but you don't change the conditions on the variables. Yeah, this example just does the same thing as previous ones, but introduces more quantifiers. And besides that, there's no actual conceptual leap of difficulty. If a question about proving a statement with quantifiers happens to be on the quiz, which it might, it'll be a bit easier than this. So, yeah, negating statements, proving statements with quantifiers, and working with summations. If I were an instructor, that's what I would put on the quiz. And that's it. Good luck on the quiz tomorrow, and I'll see you all later.